In this derivation, I show how Wien derived an analytic expression for the Wien displacement law. As mentioned in episode 1, Wien started with the low temperature form of the Planck law. Actually, Wien's derivation preceded the Planck derivation by 4 years, so I should say it turns out that Wien's derivation is related to the Planck law. The Planck law can be expressed as an energy density or a spectral irradiance. In episode 1, we used only the energy density, and most physical chemistry textbooks restrict themselves to this form. In these derivations, I am trying to balance filling a few gaps omitted in most PChem courses without going all the way into the topic of thermal physics. Here, our focus is on the peak of the Planck curve and why wavelength is inversely proportional to temperature. For simplicity of the math, I have dropped the subscript b, but k is still Boltzmann's constant throughout this derivation. For practical applications, the spectral irradiance B0 is more convenient than the energy density. It is an intensity, which explains the additional factor of C in that expression. The spectral irradiance is a point source, which is the reason that the solid angle 4 pi has been divided out. The integrated value is a flux with units of power per unit area. Wien began the derivation using the spectral irradiance. Wien's derivation began with the low temperature form of the Planck distribution. In derivation 1, I showed that the high temperature form gives the classical result kBT. The low temperature form is obtained by assuming the opposite, namely that h nu is much greater than kBT. In that case, the exponential term in the denominator is much larger than 1. Therefore, we can neglect the minus 1 term and rewrite the equation as shown in the third equation on this slide. This slide shows the derivative of the Wien function with respect to lambda. There are 2 terms because we've applied the product rule. Both the prefactor and the exponential term depend on lambda. We set the derivative equal to 0 to find a maximum. Divide through by common terms, and we can already see that this form will give a simple solution. After a few steps of algebra, we see the Wien displacement law. Since the right-hand side contains fundamental constants, the derivation is quantitative and can be used to constrain the Planck constant. The collection of terms hc over k is also known as the second radiation constant, c sub 2.